Good afternoon, everyone. So I think it's time. So let's start this section. And first of all, I want to introduce myself. My name is Jin Yang Ning from National Government University, and also all other jurists. Do you mind to introduce yourself?
I'm Chu Dang from National Taiwan University.
Hi, Roger Chu from National Taiwan Shopping Center.
Okay, thank you. And also we have 3 teams here. Let's maybe start from the reporter side. Can you please introduce yourself and all your team members?
Okay. Hello everyone. I'm your all-nighter from the Taipei Medical School, and then I'm Captain Hyun Chan, Shelly Lee, Kenneth Smoke, Alex Dong, and Justin Lee. Thank you.
Hello everyone, this is Rosetta from Junior High School, and this is Yi Cheng Han, Chen Yurui, Xiang Yizhe, Yan Yizhen, and Joanne Xi. Thank you.
This is Nawan from National Experimental High School, and this is Wang Yushen, Cai Changmen, Xiao Limin, and I is Zhang Zhong.
So let's begin the stage 1. I think first the opponent will challenge the reporter for the problem.
没有那个圈，从第三从 preparation 开始。
我已经有 challenge。
对。
Now it's preparation for the reporter. 5 minutes.
Can you write down?
因为最后做的那个梦的时候是三国志学，我已经选好，然后不是我去那个。
那老师那个 bug， 对，我们上一场他说就是他们
也被锁了，就是他记错，他系统有问题。上一场他就被锁了，然后他就说纸本只要填正确就好。
好，那 OK，
然后随便选一个。
对，随便选一个，然后
选这个。
他不知道为什么被锁。
那你们自己上就要记得是谁就好了。
知道，所以我不会在场上播。
OK， 好。
Hello everyone, I'm Hyun-Chan from the all-nighter, and today I'm going to talk about number 11, ball on the elastic band. So the problem statement says that connect two metal balls with the elastic band, then twist the elastic band and put the balls on the table. The ball will begin to spin in one direction, then in the other. Explain this phenomenon and investigate how the behavior of such pendulum depends on the relevant parameter. So the focus of this research was why do the balls spin in such manner, how do the relevant variables affect the angular and radial acceleration, and the stability of such system, and what are the special phenomena observed in this system. So I'll first talk about the phenomenon investigation with the demonstration and initial assumption. Then I'll talk about the theoretical model with the three-body diagram and the equation of the motion. Then I'll introduce the experimentation and discussion with the analysis and the limit of the theory. Then I'll move on to the conclusion to talk about the future works. So there's two key components for this phenomenon. The first is that the rubber band connect on both ends to the identical metal balls. It is also true that the constant surface with the control friction is required. As you can see, the ball spin outward, decreasing in radius, and then spin in the other way and increasing its radius. So here's some initial assumption with the dimension of the motion. So first we assume that rubber bands are the constant strength throughout. Consider rubber band having a spring constant. Rubber bands are kept at a constant temperature. No net horizontal force exerted in the system. And then no vertical movement. The flow and ball are smooth. So here's our acceleration kinetics diagram. So the origin point is the center of the mass of the system. And then the circle over there is the metal one of the metal ball. And then the radial direction from the center to the mass of the system to the center of the mass of the ball is the r hat. And then the tangential velocity vector is the theta hat. And then by summing those two vectors, we can get the V, purple V. So as you can see, some trivial calculation, you can get theta hat and r hat from the diagram, and then you can differentiate in respect of the time to get the dr hat over dt and d theta hat over dt. And then since I mentioned that radial direction and the theta hat direction is the vector sum of the velocity, so we combine into the vector sum form, and then we differentiate again to get the acceleration in theta hat direction and the radial direction. So this is dynamics. So I want to talk about that. The first force equation is talk about the radial direction force, where we consider the tension force and then also kinetic friction force. And then this ma of r is representing from the previous slide acceleration. Previous slide acceleration of the radial direction. And then move on. So the second equation is talking about the theta hat direction, where we consider the static friction, and then the theta acceleration theta is also coming from the previous slide acceleration formula in the theta hat direction. And the third equation is talking about the torque. So K delta phi in the torque torsion force, and then the FFS represents the static friction force. And then by manipulating, we can get the static friction force equation, and we can get the acceleration to phi. So here's the equation of the motion. So as you can see, those three motion of the equations are coupled. So we cannot solve this analytically. So we need to use the Python to solve this numerically. So we use the Python model over here, and then there's some internal variables that we need to set at the beginning. As I mentioned, we need to solve it numerically. So these variables over here represent the variables that impact the motions. So by changing those variables, we can get the two corresponding graphs directly. So here's the first graph that I will talk about. So this is the angle versus time, and then as you can see, it has an underdamped harmonic motion throughout. And then there's also next graph where it talks about the radius versus time. And then this is also have the underdamped harmonic motion, but this one will reach equilibrium faster due to the opposing friction force in the radial direction. So here's our experimental setup. So we use the clamp to control the number of the turns that we want to investigate. And then we also vary different sides of the ball with the mass. And then we also test different rubber band, because each rubber band has their unique torsion and spring constant. So changing those rubber band is crucial to the overall relevant parameter. We also use the tripod and camera to investigate what's going on in the system of interest we're looking forward to. And then this is one of the many frictions that we test. After filming the video from the tripod, we use the tracker by tracking on both left and right ball. So by doing that, we can find the center of the mass of the system, also with the balls, and then we can also find the theta hat and r hat. However, when you find the r hat vector, you need to use the Pythagorean theorem, but then the Python coding has a problem for the arctan function, where it resets 0 to every 2 pi revolution. So I use the increment for loop to prevent the happen to make the more representative angle versus time graph and equations. So the first experiment I want to talk about is the proportionality between the omega r and number of the turn, which is also n. So from the beginning, we approached with the energy analysis by saying that the total kinetic energy is the sum of two balls' angular kinetic energy plus the system angular kinetic energy, and then that is also equal to the torsion energy. And by plugging into the inertia of the two balls with the system, we can get to the here point where saying that omega r is proportional to the number of the turns. So this graph is trying to do the error analysis between the theoretical one and then the empirical one. So as you can see, as I plot maximum omega r, and then here's the number of the turns. As you can see, the graph up here to show a linear line, and then the data are within the 2 standard deviation of the graph, as you can see in this arrow. So this empirical data support the theory that omega r and then number of the turns are proportional to each other. The next experiment we did was considering the mass. So we tried to find the maximum angle past equilibrium versus mass. In theory, by putting the maximum angle past equilibrium in degree with the mass in kg units. And we tried to find the mass by approximating the theoretical mass graph by changing the mass in the numerical program and finding the largest values being past equilibrium. The mass of the rubber band is negligible in the calculation as you get less than 1% of the total contribution of this calculation. So we do not have the prediction equation for this one, so we need to also solve numerically through the Python coding. So here's the error analysis for the previous experiments. So as you can see, the blue dots are the experimental, and then the red dots are the theoretical data. And as you can see, most of the data empirical data points are within the 2 standard deviations away from the theory. So there's no statistical evidence to reject this claim. And then the theoretical curve may only be accurate for the certain parameter, as we only find those values from numerically, and we do not have the representative equation to following this general trend. So this is the crucial graph I want to talk about. So this is the angle versus time. And as you can see, the blue part is the theoretical graph, and then the red part is the empirical graph. So when we try to find the R-square value, it's not that high. But the lower R-square value doesn't mean that it does not have the good quality of the graph. As you can see, it's still qualitatively agree where we still see the resemblance between the empirical one and the theoretical graph. Also, the general lines are still aligned, and then the lower R-square value could be just caused by the shift due to the towards the right side of the empirical one. The smaller peak of the experiment, as you can see, this is smaller than the theoretical one. This could be due to the energy loss because of the opposing force underestimated in the theory. So, for example, it could be like kinetic friction due to the slipping, or it could be uneven surface that's causing this underestimation. So this graph is talking about the radius versus time. So this one also, I tried to analyze error analysis, and then the R-square value is also low. But as I mentioned, it's not an indication of the quality of the graph, where though still qualitatively agree with the general trends, and that this slower change of the radius than expected could be due to the underestimation of the friction of the radial sliding and much smaller peak than expected due to the unstable buckling effect. So I would like to talk about the buckling effect. So as you can see, the rubber buckle when you go to the certain number enough of the number of turns. So here's a setup that I'm trying to test the buckling effect. So here's the graph. So the nature of the radius in the y-axis is the function of the phi, because the numbers of turn makes r shorter. So when the rubber band is horizontal, we observe that the buckling effect that decreases the natural radius in the rubber band. Although it is not buckled, the twist makes the radius smaller but not drastically. The place, amount, and twist necessarily vary in different experimental trials. So as I mentioned, in vertical system, there's no buckling effect because gravitational force unbuckled the rubber, where in the horizontal system, there's still a buckling because there's no other force that unbuckle the buckled parts. So buckle effect crucially affect to the natural radius, where this Python code is taking care of the gravity consideration, and then the curiously rubber band that buckles do not cause a decrease in the angular velocity in comparison to those who do. So we hypothesize that the buckling creates a linear outward force that is originally not present. And then also it could be due to the ratio of the mass between the rubber band and the ball may be too small so that the buckling effect has the little influence in the overall shape. So here's some example for finding the stability of the system. It's called Laplace exponent, where the function tells you whether this given system is stable or not. So here's a function that you can find the value. And then this is a graph that if you put some certain information into this exponent, it will give the stable region over there with the angular velocity. So the conclusion. So we assume that the static friction is above a certain level to achieve negligible slipping in the theta height direction. Our theory will still work relatively well for the low friction surface due to the high ratio of the rolling to slipping ratio. We also want to include causing equation of the motion and stochastic stability, where it tells me whether the given system is stable or not. And it does not consider the chaotic buckling effect. However, the buckling effect seems to have no major influence in the radius of the system. So here's some equation of motion where we derived and talked about. And then here's the graph where you can see there's some under-damped harmonic motion in angle versus time, and also the radius versus time versus angular also has some damped harmonic motion where it reaches equilibrium faster than the angle versus time. So here's a reference, and thank you for listening.
Could you please go to page 5? So how did you connect your band to your ball in your experimental setup? How do you connect your band to the ball?
We use bones to connect the ball.
Okay.
Rubber band.
Okay. So so you assume that the rubber strength of the rubber band strength is constant. Yes.
Sorry.
So you assume that the rubber band have a constant strength.
Yes.
And do you agree that the rubber band strength will be related to the length of the rubber band?
Yeah, it does.
Okay. Can you go to page 9? Here the origin will be the center of mass, right? Of the system. During your swing motion, does the center of the mass move?
No, it's fixed because I can also show you later that we also test rolling without friction.
Okay. Can you go to page 10? So here, yes. So in this system, it of course is affected by friction, right?
Yeah, it does.
And it is static friction or
static over there, kinetic over here.
Okay, so both.
Yeah.
Okay. Page 18, please. What is R here? The R.
R. Oh, it's the pole of the radius.
Ball. The radius of the ball.
Yeah, and this is the pole of radius of the system.
Do you mean the center of mass of the ball to the center of mass of the system?
Yeah.
Okay. Can you go to page 19? Why is does the air ball seem to be all the same?
Yeah, it's the two standard deviation away. So
Okay.
what I did is I plot into a normal distribution, and I find the two standard deviation I put into the error.
Okay. Page 22, please.
Yeah.
What causes the shift to the right of the experimental?
This is what I mentioned in here. These are what I mentioned that cause the shift.
Okay. Thank you. Now, please. So I'm Joy from team 9120, and I will be the opponent for number 11. Okay, next page. Okay, so problem statement: connect two balls with an elastic band. So here we're going to focus on some crucial points: mass of the ball, diameter of the ball, mass of the band, the length of the band, and K, which is the coefficient of the band. And in their case, they use rubber band, and we're going to discuss whether the force created by the rubber band is constant. And also we're going to discuss about the period of the motion, because yes, okay, next slide. So summary of the report: they have very good error analysis, and they have a very good theory, and their experiment method is also very good. So they use Python and to calculate the numerical value, and they also give a concise explanation on why their data doesn't fit their theory. And the concept that they lack explanation of the phenomenon itself. So they started their report going straight into the theory. So I did not see a lot of observation video. And also, there's no definition of the angle and some specific terms such as the radius. And also, they don't have the connection between the. I believe that the connection between the theory and the conclusion can be better. Okay, so points to be discussed. So the phenomenon explanation, we're going to also, of course, in this system, there's some force that apply to it: friction and probably normal force, gravity, and something like that. And we're going to talk about how the rotation will affect it, and also the spring. And okay, in their theory, they use 2D coordinates, and I'm wondering if there will be a possible three-dimensional force or movement, and also the whether it is static or kinetic friction, because the two of this can only occur one at a time. So, and also, is it rolling or is it sliding? And also about the chaotic buckling effect, they probably have to elaborate on that. And okay, so in the experiment method, they use coding and tracker. And however, I believe that something they might improve is to quantify the force, and for example, to measure what the force of the rubber band is. Yes, and for the parameters, I believe that they use different balls and different elastic band, and we're going to discuss about how they will affect it. Okay, So let's move on to our discussion. Okay. So could you please go to your page? Yes. Okay. So so just to be sure, so you start this moment by twisting it, right?
Yeah.
So you are sure that the center of mass is in the middle, and then so you just release it and it starts spinning, right?
Yeah.
Okay. Great. Okay. So you mentioned that in page 10 that one of it is static friction and the other is kinetic friction. Can you elaborate on that?
Yeah. So may I use the board?
Yes.
So in the bowl, there's two bowls. Center of the mass system, and then the spring force will push it inward.
Yes.
So that the sliding, this force will make the ball sliding rather than rotating without slipping.
Sliding towards the center of the mass.
Yeah, as I draw in here. So this will make the friction kinetic rather than static.
So this will be kinetic, and where's the static one?
Static in the theta head direction.
So the ball is rolling, right?
Yeah.
The ball is, so do you know that the rubber band is twisted, right? And it's also lengthened and twisted. So besides it going in towards the center of mass, it's also providing a force for the ball to rotate. And how can you be sure that it is rolling but not slipping?
Okay, so I got the empirical analysis calculation. I was introduced, but I was running out of time. So here. So first, I found the threshold coefficient of static friction, and then once this part is rolling without friction, the higher coefficient will also rolling without slipping.
Sorry, what's the y-axis?
Y-axis is the max angle past equilibrium.
So where's the equilibrium?
Equilibrium is when the band is not twisted. It's the linear line.
So it's stable, and you just put it on the table.
Rubber line is usually like twisted, but this one equilibrium is just a straight line, not twisted at all.
Okay.
Yeah.
Okay.
So do you want the number? Because I also got the number where it's showing that rolling over the slipping rate is really high, so that we're proving that ball are rolling without slipping.
Okay.
Yeah.
So ball rolling without slipping, and so you are sure that it is rolling because you measure static friction. Okay. So I realized that you said that the force of the rubber band is constant.
Yeah.
And so I understand that normally when we pull a rubber band, we pull it linearly. So, but in this case, we are twisting it. So it not only changes in the linear component, but also twisted. But so when it twists, can we assume that it's actually like lengthening?
Yeah. So here's a graph that is showing that they have the linear relationship of the stretch. So we stretch and then we measure the force, because you're talking about we do not consider force, but we also measure the force.
Is this the force on the linear component or the rotating component?
Linear component.
So did you measure the rotating component?
No, I didn't.
But I believe that it is for this motion, because it is rotating. So the ball itself, when the ball itself is rotating, is very important. So did you ever consider trying to measure, for example, if you twist it for 10 times, and what's the restoration force of the rubber band?
No, but instead we did a different approach by talking about the natural radius with buffering effect. So is that answering your question or no?
What I'm looking here for is I'm just wondering whether, like, for example, if you can use a torque pendulum, and you can like twist the rubber band like for 10 times and then measure the force, right?
Yes.
And then once you get the force, and then in your experiment, you can track your data and say, oh, in this experiment it's turning for 12 times, so the force is this, and then see, like for example, how this force will give the ball an acceleration, and then let it go back. You know what I mean?
But to answer your question, we plot angle versus time, and we can find the mass and we can also find the inertia. So I think we can find the torque from here by I and finding the angular acceleration from this graph.
Also, you can find your torque by this.
Yeah,
thing.
because we have the angle information, and we also consider the mass with the mass of inertia.
So-
So I think we can.
Oh,
find the
so
torque.
you use a moment of inertia?
Yeah.
So,
with the mass.
can you tell me how you calculate your moment of inertia?
Moment of inertia.
Yes.
So as I mentioned, we do not have the prediction equation, so we use the Python to.
Can you, for example, write down how you consider this
Okay.
moment of inertia?
So theoretical one, I change the m over here and then run the Python, and it will give me different graph.
So
that's
you
why-
didn't use any simulations such as mr squared, like something like that. You didn't use this kind of equation. You just plug it into Python.
So that's the theoretical part. And the empirical one, we measure the inertia.
No.
Is it,
I mean, like, is there any part where you got something like for example, this or
oh yeah.
this?
Oh, you mean did I
Yes.
consider the inertia?
Yes, the moment of inertia.
Here.
Okay.
Energy. We're trying to find the proportionality between the omega r and number of the turns.
Yeah.
And we use
So this r is the radius of the system.
Yeah. Oh no, r sub b is the ball and r sub s is the system.
Okay, r sub s is a system, and is r sub s a constant? No.
It is. No. As you understand, the phenomenon is increasing and
Yes,
decreasing,
it's
so it's not
increasing,
constant.
Okay. So did you derive, for example, what the force of because this is not a constant, right? So this will change through time, right? So did you derive an equation that is related to time? Like, for example, what the inertia is related to time? So that because everything in your graph is related to time, so maybe you have to derive moment of inertia.
So this is the mass versus any maximum angle, and maximum angle is proportional to the period. So is that answering your questions?
Okay. Okay, let's move on to the next question.
Yeah.
So you assume that the ball is smooth, right?
Yeah.
And the ground is smooth?
Yeah.
So, and there is still friction?
Could you repeat one more time?
Yeah,
Are you
so
saying that
the,
uneven or it's smooth?
Smooth. So, ball is smooth? Is it?
No. As I mentioned, I test multiple surface over here.
Can you go to your
Yeah.
assumption?
Assumption.
Yes, your assumption page. So let me see. Yes, you said that the floor and the ball are smooth. If it is smooth, there wouldn't be friction. Right?
Smooth meaning that it's not uneven.
Oh, I
Yeah,
see. I see.
yeah. Sorry for the confusion.
Okay.
This makes confusion.
Okay. Also, you mentioned there is no vertical movement. So as I see, you used 2D coordinates. So did you observe anything that goes three-dimensional? Or
No, as I mentioned, we test in even surface, so it's only rotating in the 2D motion. So we
Okay.
cannot consider 3D motion.
okay. So okay, let's move on to the next one. And so did you have any part where because you talked about the what's that? The rubber band will twist together. Yes.
Are you asking me about the torsion or?
Yes, the part where you said that the rubber band will twist together, and then at the horizontal component there will be a thing.
Oh,
Yes.
yeah, buckling. effect.
Buckling?
Yeah.
So did you investigate, like, for example, how many twisted, what's the maximum twist before it starts buckling? Because once it starts buckling, it's chaotic and unstable, right?
I think that's not important. As you can see that every spring has different materials and different density, although we assume that it's forces strengths throughout.
Yes.
So we cannot really measure each rubber band's number of the torsion makes it buckling effect. And it's not like every time happening, it's like occasionally happening. So we cannot always generalize that into the certain number of the threshold that makes it buckling effect.
Occasionally it happens. So when does it happen horizontally? Right? Because for your observation video, I cannot see buckling.
Right. So it will be different. So this is the graph where this degree meaning that how many rotation I give. Like for example, the maximum I gave was more than 10,000 angle, which is really many.
And was your sorry, just a question. Was your degree when the ball is rolling, or is it the whole system spinning?
The torsion. So
the torsion of the rubber band.
V is the torsion. Yeah.
Of the rubber band.
Yeah.
Okay.
So you can see as a top view of the ball that rotating one revolution is 360 degrees.
Okay. Okay. Now we can move on to the last one question. So did you consider the cycle of this motion, because it spins from here and then to here and then to here, right?
Yep.
So it spins and
So that's why we talk about the damped harmonic motion.
Yes.
As you can see that this is increasing in negative direction in
So-
one direction and going the other direction, coming the other
So
direction.
what parameters of experiment did you do that will affect the cycle of this motion?
So mass, we talked about mass, and we also talked about the angular velocity and the number of the turns.
Okay. So I guess that'll be.
Thank you.
Okay. So quick summary of this discussion. Basically we talked about how the strength of the rubber band, whether it will maintain through when it's lengthened or it's shortened, and then they made some assumptions. And also they believe that and they give a clear explanation about how staggered friction, and then they assume that because it is staggered friction, so it's rolling. So the ball is rolling, and I thought that they could quantify the force, which they did using another method. And okay, and also that, but they didn't give for example, a time related equation to, for example, the moment of inertia, which changes through time.
So question for both of the reverter and the opponent. I want to ask, do you think the buckling will influence the disturbance?
As I mentioned in the conclusion, buckling effect does not influence into the omega.
I don't think in with our open share we didn't see the common effects, so we finished.
Okay, then the next question for the recorder. I want to ask, how do you change the radius without changing the mass?
Radius of ball,
Yes,
just use different type of balls.
and without changing the mass.
Yeah, we can change the density of the mass of the ball.
So next question, do you think the motion is periodic?
Yeah, as I mentioned, it's under damped harmonic motion, so it's periodic.
Can you tell me if the lens become bigger, what will happen? If the lens of the rubber band become bigger, what will happen?
Because lengthier the rubber band it makes the force smaller, so it has a smaller kinetic friction energy, a friction force into the radial direction.
What's your opinion on that?
The longer the rubber band is, the force will be greater. Yes. Is that what you're asking?
How would you describe the energy transformation in this whole system?
So I mentioned that here, torque energy is equal to the angular energy of the system and the two balls. And rubber mass is negligible, so we did not consider the kinetic energy.
So it's more like a electric potential energy transferred by the rubber band, and then it changes into the spin cycle of it. Yes.
That's all my questions. Thank you. am going to review problem number 11, both on an elastic band. So this is our main focus. How can the movement of both balls be theoretically explained and calculated? And how does the total energy of the system depend on time? Where do energy losses occur? And very different parameters of the system, and explain how this affects the experiment. So here's a summary of the report. For the understanding of the problem, a rubber band connects two balls are on the constant surface. And for the theoretical analysis, the acceleration kinetics diagram and the dynamics analysis and motion equation is associated with the friction. And for the experimental confirmation, they track both sides motion in order to find out center of mass and other parameters, and the relationship between angular velocity and the turns, and the relationship between the mass and the angle, and also the radius and time, and the chaotic buckling effect, and compare buckling and the unbuckling. This is the pros and cons for the reporter. For the pros, they have a clear introduction of the problem and the observation video, and they use for analysis and turn to quantify the results, and their experiment to verify the results regarding energy loss and buckling effect, and they get the accuracy variables turns the band and mass of the balls and the radius of the balls. And for the cons of them, they miss the address of a physical phenomenon for the damping, and no theoretical consideration is rolling friction and the sliding, and the lack of investigation on energy transformation and fatigue, and they have a clear graph. And for the pros and cons for the opponents, they have a clear questions and understand the experiment well, and they have sufficient use of opposition time, and the legitimate question asks on the further understanding of the theory, and they focus on what the reporters say. And for the cons of them, they lack of comments of the reporter, and they should focus more on the comparison between the theory and the experiment. And here's a discussion, and for the opponent asks, can you elaborate the rolling motion? And reporter responds, just as their experiment data shows its rolls because static friction, and we agree with the reporter. For the next one, they ask, do you consider rotating components? And the reporter's response is not, and we agree with the opponent. We think that should be taken into consideration. And the opponent asks, how do you calculate the moment of inertia? And the reporter said no simulation, and they use half times inertia times angular velocity, and we agree with the reporter. And for the next one, the opponent asks, do you consider 3D motion? And the reporter's response is that they just consider 2D motion, and we agree with the opponent that we think 3D motion should also be taken into consideration since it is 3D motion in the real condition. So for the next one, the opponent asks, do you consider a cycle of motion? And the reporter's response is yes, and that will cause by some instabilities, and we agree with the reporter. So for the midpoints, they assume are on page 18 for the system is a constant, but it is not. And for number 2, the fatigue of the band they didn't consider it, and for they didn't consider the rolling friction and the elastic coefficient. It may make the length changing, and they can't just consider the torsion coefficient, and they need to describe more about the energy loss, and the damping cost of motion is not periodic, but they both think it is periodic. So this is my review. Thanks for your kind attention.
So to revert this conversation, first we talked about how does the we first talked about how does the acceleration kinetic diagram works, where we talk about the radial and then also data head direction with the force with the torque analysis, where we get this three coupled equation we to solve numerically, and then we also talk about the motion in radial direction in both radial and data head direction, and count for the friction. For the experiment, we talked about omega r is proportional to the number of the twist, and then also the angle versus time and radius versus time. And as you can see in the graph, it has under the harmonic motions. And then for the radius versus time, it reached the equilibrium due to the opposing friction force in the radial direction. And we also talked about the chaotic unstable buckling effect. And I briefly introduced about this stability force function for the future work that I want to improve by testing this experiment in the stable conditions. For the discussion, we talked about center of the mass need, constant location. It in our case, it is true because we proved that it's rolling without flipping friction. And the kinetic friction energy radially and static friction energy in omega theta head direction. And then we want to say that the floor and the ball are even, so there's no free motion. And then the moment of inertia value we find empirically by finding the torque from the Vernier probe, and then we track the angular acceleration, and then we divide by to get the inertia for the empirical. And then for theoretical, we use the implicit variables in the Python to find the empirical theoretical one. Also, we talked about last for the Buckley effect, and then the max twist omega. So this is for my end of the presentation. Thank you for listening.
So now it's time for the question from juries. So please.
So question for reporter, how do you connect the rubber band to the ball?
Sorry.
How do you connect the rubber band to the ball?
So we used for the rubber, we used sticky foam. So we attach the rubber band with the foam.
Using what?
Bond.
Bond.
Yeah, bond.
Do you think that for the report component and the review, do you think that will play some critical role?
I'm not sure about what their sticky foam is, but if the first of all, if it affects its math, then of course it will affect the experiment. And second of all, if the contact point is not, for example, perpendicular to the surface, and it is somehow not perpendicular, then it will affect the rotating motion.
So we think that symmetrical will also affect the moment on the inertia. So we think it may cause a real effect of the result.
Sorry, Professor. I want to clarify that we use the caliper to measure the center of the mass. Then we connect those 2 points by indicating at the beginning, and then connect using the bone to connect the band for those metal loops. Yeah. We use this bone, and then we use the caliper to point out the center of the mass in the front view, and then we connect those 2 points with the bone and the rubber bands.
Is there any other question from jury? Still, I have one question for all of you, because I think also the reviewer point out that we should consider the damping. So I'm thinking that if the experiment is carried out on a not very smooth surface, with large friction, how it goes.
So it's going to be under them, and then the damping part is increasing more, decaying more fastly.
And yes, the same as a reporter, and also I believe that first of all, a 3D model will need to become considered. Yes.
How about review?
So for me, since damping will causes the motion is not periodic, and but they all mentioned in my short question that they think the motion is periodic.
Thank you very much. And I think now juries. Please, I'm sorry. So let's begin from the school for reporters. So it's 7, 9, 10, 8, 9.
Thank you.
So now is the score for opponent. It's not 7, 8, 10, 7, 7. Thank you. Finally, is the point and the score for reviewers. So it's 7, 7, 9, 7, 8. Thank you very much. So we will take 15 minutes break before the next stage.